Thanks for checking it.
It's a $700 version as opposed to the $200 version.
So it's got a protection on the on and off button. It's good.
Matt picked it up.
All right. Today we're going to talk mostly about castings. I have a few examples, and I'm not going to go into the very detail of scientifically what's important in casting. We will do that a little bit on Monday morning. I'm mostly going to give an overview. And before I do that, I want to reflect back on our introduction lecture on Wednesday when we talked about the World Trade Center. And there's a reason. It's not that trying to recover something that we've already discussed. I think I mentioned I worked on the leading team for the detailed investigation by NIST, but it's such a long process of engineering analysis that I had to realize yesterday that I didn't know all about it, even though I was really part of the team who analyzed it. And I want to bring that up a little bit, connecting with the lectures that Professor Eger is giving in the context that as things get more and more advanced, the more you work on something that is sophisticated, you tend not to know everything about it. If you work for a big aircraft manufacturer, you're going to be in this division working on the wind design, and they'll make almost a special effort not to tell you everything else about it, or at least not have you worry about a lot of other things. So everything gets into smaller departments, and it's very rare to have engineers that have very good in-depth experience in many areas, but it's useful. It's very useful, and hopefully you'll see in the context of this class, when you're able to talk about what is the load applied on the material, and you're also able to know how it's made, and what resulting for the making of the material, the resulting characteristic, it really helps you. And that could be specific to an area that you're interested in. Say you're interested in renewable energy. There was somebody after class on Wednesday say, I like composite. Well, the wind turbine industry has been growing all these composite manufacturing technique to a very level of sophistication. So what I tell a lot of times students when they come with projects or ideas, say, well, how about you look into, if you want to build an engine that's efficient, well, maybe you go to the Lenmower industry, because they make the entire motor for $100. So they should be able to make you a very cheap engine. And I think that it really can help you, not try to reinvent the wheel on everything you do. But that's a little bit, so that was one aspect for coming back. The other aspect, if you remember on Wednesday, I said in failure analysis, it's very useful to go over the details of the evidence. It's very nice to use, first scientific principles and say, well, like Professor Eger was very able to say quickly, well, it didn't melt. Okay, good. So that's one thing checked. And then the next step is, okay, well, so how exactly did it happen? And you can have many, many theories. Some people were thinking maybe they took the bolts out ahead of time. It's serious. I mean, the conspiracy was associated with that. People were thinking, well, I don't believe it the way it's falling. It shouldn't fall this way. So you get to this more advanced level, and then starting to look again at these floor truss or joist, and at the beginning, it was really just an idea. Perhaps it was a better hypothesis, but it really is just an hypothesis until you can, if you can, look into the data. And this video here goes in great depth, because one of the big criticism of this pulling theory was, okay, well, why did it tip over? Why did the entire tower tip in the end? That sounds like a buckling, and so that sounds like it's the main column that failed first. And I think the final rebuttal to that was, well, yeah, one side pulled more, and that's the entire wall that buckled because of the pulling action. Now, the reason why I think it's becoming more of a really a proven theory as opposed to an hypothesis now is they looked at that wall using an image analysis, and it was gradually coming in. So let's go over the theory and then the evidence. So you pull on those joists. Oh boy. Okay, so this is doable.
Well, that's back.
Yep. Is this one? No, it's not this one. So it's part of this. Good. So there was essentially an horizontal beam connecting these trusses, and that's what you see getting pulled. So the model has it going in, a fair amount, probably about 3-4 feet. And that's actually the type of measurement that they were seeing gradually. It wasn't the same amount on each wall. You see 1 minute before it collapsed, it's really not straight. And this is between the stories. So it's very localized. When it snapped, on this magnified view, I think you really see it coming in. So the idea that there really wasn't the spring action that is essentially the basis for the theory, well, it sounds really like it. So, from my standpoint, I didn't see this nicer set of images until yesterday, but to me, it sounds like it closes the loop. You apply all the principles of physics, you do the detailed computer analysis, and then when you look at the structure, it's falling in the same sequence. And so one wall was recorded at 50 inches, so 4 foot of pull in just before it finally buckled. Now, at the same time, the other walls were not as buckled, and that's why they didn't fail first, and the whole thing tipped over. So you don't have to believe it, but at least I feel like I covered the loop, and it just points to, I was very interested in this project. I was involved in it for probably a 2-year period, but I never got to see the very final output, and maybe to some extent there's still some things we don't know, but I think we do understand a lot about it. And if you recall from Wednesday, insulation, so fireproofing of building code has changed significantly, and then the impact resistance as well. So I had involvement in the Liberty Tower that was put on after, and they had a lot more analysis done in terms of sideway impact energy, just because it was a high-profile building. I don't think that it's part of the typical building code, but they were requirements for this specific project. So we learned from our mistakes, right? We could have avoided this. I mean, not the terrorists coming, but
who was thinking about this scenario when they were building it, though,
Yeah, that's true, and so that's a very good point. When this was built, it went on a bid. And typically for a building, even today of this side, even if it's a nice one, they pay a little extra for the architect to come up with something that looks good. But as far as the structure, typically it's building code. So you can be the best structural engineer in this country and still have to provide your services on almost a fixed cost basis because your job is to apply the code. Unfortunately, except if it's a very high profile situation. Now they'll say, oh, well, in addition, we want this. Or the architect say, well, I want to suspend that 50-foot long fish. And then you get to do some more sophisticated analysis that is not part of the code. And there are sections of the code sometimes that allows you to do alternate calculations, and that is sometimes where a good structural engineer can do something more advanced than applying the basic code equations. Any other questions about this World Trade Center? That was very good.
Sorry, your YouTube recommendations are going to be messed up for the next month.
Oh, no. Well, it's funny. I don't think I watch it very much, so I don't have the time. So it's okay. So let's go back to what my job is for you today. The casting, and I don't know why. Good. We're starting there because most metals, you come from the oxide a lot of times. So iron oxide, aluminum oxide, and you make the liquid steel. I'm not going to go through that with you. First of all, I'm not the best person to speak of it. So we're going to start with a liquid metal that's already been refined. So the simplest process, what was done before the invention of steel, was the cast iron. So with cast iron, you melt it, and you pour it in a mold, and you get your parts. It's still used today, not just for cast iron pans and cast iron stoves. This fitting here, I'll circulate some of these, was cast. For the reason that it's a relatively complex geometry, and to the extent that the material used is inexpensive, you're okay to just make it a little thicker, and you build it. You won't put that fitting even in a car or an aircraft, but you'll put it in a building because you don't mind the extra weight. So that's an example of cast. Anybody tell me right off how this was built? Here, extrusion, casting, it's none of them. That's why I ask. I don't.
The front part has been kind of welded to the lower part.
Yes.
Yeah.
Yes. So
Because the beads are visible and all.
it's all wrought products. So this was built using 5 different stock of steel. The tubulars, so with a hole in it, or the smaller diameter is essentially a solid piece of steel that's wrought steel. It's essentially steel that was cast and then processed through high temperature deformation. So it's very ductile, it's very homogeneous, it's a good quality steel. We'll talk about that a little bit next week. But the emphasis is, I think, hopefully, that's one of my objectives for this semester, for you to realize that, some stuff makes sense to be cast, some doesn't. In this particular case, if you try to cast the steel, it's very high temperature. So by itself, it can be done, but it's a difficult process. And then if you need to change any of the dimensions, now you have to make a new mold and you requalify all your processes. Here, you go to the store and you buy the different sizes and you weld it together. And if somebody says, well, I want 10 more, well, you cut a few more, put a few welds, and that's it. You can make the new one. The other advantage is because the metal has been deformed and homogenized, it's got more reliable properties. It's less susceptible to cracking. And we will go into more details of why that is important. What about this one? It's a bolt head.
Bolts are generally forged.
Mm-hmm. Yeah. Why? So let's say you start with a plain rod, right? And your challenge is to put this head on. So how do you think you'll do the head is the general question. Do you weld the head? Do you
Machine it.
machine it? Yeah. That will require a lot more steel, huh?
Yeah.
So let's rule out casting, okay? This sounds like maybe we can do this without casting it. I don't know of any cast bolts.
Yeah.
You press the end, so you cold forge the head from a rod. That's very common. You can do it hot in some conditions, but the cold pressing is less expensive. And you have to do it in multiple steps. So you start flattening it a little bit, then you flatten it a little more, and then you flatten it a little more. So the bolt head is a little bit like a rivet that we put on aircraft. So you start with a round material, and you keep building up that head through multiple operations. And the good advantage of it is the section that sees the more stresses, the shaft of it, is the original wrought material. It hasn't been changed. If you were to try to use any sophisticated joining process to put the head, then all that joint will be part of the loading path of the bolt and reduce the capacity. In this case, we don't really see issues around the bolt head. First of all, there are no treads there. So if you have a bolt that failed, like this one, it's on the side where the tread and the knot engage together because you have a notch into the tread at that location. Yes?
Do you know how much force or pressure it takes to press this head down? I imagine it takes
It's
several
number
passes.
written
Yeah.
on the head of that. Generally, there's a number written. What gives the classification?
So it will give you the strength of the steel. This is typically high strength, relatively high strength steel. If it's a grade 8 bolt, it will resist 150,000 pounds per square inch. So that's the type of magnitude you're looking at. You need to hold it. If you just try to, it's just going to buckle on you. But yeah.
To answer your question further, the deformation processing module goes through that. And in fact, if you're just pressing on something to try to flatten a pizza dough into a thinner pizza, it's about equal to the yield strength of the material, minus the friction. But if you're talking about something like that, where you've got
It's constrained.
aspect ratio that's higher, it can be up to 3 times that force. So your tooling could have stresses on it, if that was 150 KSI steel, of 450,000 pounds per square inch, which is why that was hot forged, one that size.
Okay.
Or warm forged. It could have been warm forged.
All right. So now is another one. You're good, so you don't say it.
Well, I'm just trying to point out there is
No. Yeah.
That's the type of thing you're interested in.
Yeah, forming.
The module is for-
And it's called forming, right? And that was a couple of years ago. Yeah.
Well, it's actually deformation processing,
Yep.
which is back off the name, back off.
Yep.
You should have started with that one. That one's easy.
Yeah?
Yeah.
So,
That's cast with like a finishing pass to finishing.
yes. So, thank you, Jerry. We'll pass the lecture note. We'll see. I'll ask you guys after a couple of lectures if this is any useful to you, because it's on the stellar. I don't mind killing trees because they grow back. I'm Canadian. But if this is not useful to you, we don't need to do this. Okay, 2 more here. And then they mostly work in healthcare, actually. To support the pulp and paper. You know.
The guys who cut themselves with chainsaws.
Yes, exactly. Okay. All right, so the last one is a sand cast component. It's part of a suspension system. I'll show it to you later for all-terrain vehicles. And you guys were correct. It was machined at the where you connect the bearings. Because you don't get the type of precision needed for this type of joint. And it's the same for this one. This one, I don't know why I didn't pass it around. You see on the inside that there's a little bit of residues. There's probably sand particles there of some sort. I don't know what it is. But they had to machine the treads out. These are not cast. So it's a cut view, and essentially you have 2 pipes already connected, and then we cut after putting the pipes in. So there is a lot of volumes of parts made especially for water systems that are cast. Valves, fittings like this one, for the reason that it's a fairly complex geometry, You could make this almost solid and drill holes to it, but then it will take a lot more material. It'd be a lot of machining. So what they do is they do a rough casting, and then they come and improve the dimensions that are needed to make joints with other components. Even though it doesn't give you the best properties that we go over later, because it's so easy to take the mold, put it in, if you can get enough quality, and we'll talk about how to do that, then it is commercially favorable. It's the best alternative. Now, who thinks the cast iron is brittle? Yes, it is. Now, I do want everyone to remember that it doesn't have to be. So it's not because you're casting iron that you are left with a low ductility. There are small changes in composition and heat treatment you can make to change the internal microstructure from something that cannot really be deformed to something that is readily deformable. So this nodular cast iron type is also called the ductile cast iron, and it's used a lot for water pipes because, again, you can cast it, but you also get the benefit of isolating the hard particle in balls. That's why it's called nodular, and therefore you still get your deformability. So these are examples of large diameter pipes, and if you go to any plant and you see something this big, a lot of times it was cast. It allows you to do the flanges at the same time as the body of the pipe. So this is very suitable if you're trying to connect multiple components together. You do need a flange to put the bolts on. In volume, it's a very large industry. It's not something that's used a lot for anything in advanced manufacturing, but if you need something big, these are the types of option that you're looking for. So why do we use the castings? I think that the general answer is because it's going to not cost as much. There's almost nothing. It cannot be machined. There's almost, now our additive manufacturing techniques are improving, that there's a lot of things we can build from scratch as well. So cost becomes a main driver. And I think if you look at that aluminum knuckle I circulated, a lot of time a combination of not needing the best properties with a complex geometry is a good application for a casting. I want you to keep in mind that casting is done most of the time as part of making a steel product or even plastics. I will probably spend 1 or 2 lectures a little bit more specifically on plastics even this semester, just because I know that it's of interest to at least half of the students. Although you should keep in mind, just yesterday I had a call from a headhunter for metallurgists. I mean, it's not because we're teaching something that very few people teach that it's not needed. There's actually very few of them that have the experience on what we are talking about in this class. A lot of people have moved into bioengineering, biomedical devices, and so if you do have an interest, I think there's always going to be a need for more traditional structural material analysis and engineering, including the big companies. So that knuckle, we talked about it a little bit. What it does is you have the bearing for the wheel in the middle, and you see it connects here to the control arm system of the small vehicle here. Does it really need to be lightweight? Well, that's up for discussion because it's not really part of the wheel itself, so it doesn't get accelerated. But it's part of an assembly that people try to make light. These vehicles will weigh something of the order of 800 pounds, and therefore each 3-4 pounds you add per wheel of extra material does make a difference. And they get compared from manufacturer to manufacturer for that difference. especially snowmobiles. If you can have a great, nice and smooth snowmobile, but if it falls too deep into the snow, nobody's happy. So it's to keep in mind that even though it's recreational, they do need some different characteristics of performance. So they went to an optimized geometry and a relatively low strength material because it was as cast. Their production cost was fairly low, but one problem they had here is when people had rollovers with the units, sometimes they will break the parts and then go back and complain that it's because the part broke that they had an accident. And that's a part of failure analysis that is sometimes unfortunate for a manufacturer because it's very hard to prove one way or the other. The only thing that's known for sure is your part broke in two. And when exactly that happened, you don't know. So there is, I guess, a little bit of a wisdom here that if you anticipate as an engineer that people will abuse your product and it is a consumer product, it's sometimes much better to let the parts deform as opposed to actually breaking. And I've seen this more recently with come-alongs. So you make an assembly for pulling that has a bunch of components. You can use some castings in it, but if it breaks, so what's the problem? You know, did you overload it, or was it really poor quality to begin with? And it leads to bad consequences if you all of a sudden it breaks. It's better to have something deform and you can't crank it anymore, for example. You know, you bend the handle, you can't use it, then being able to essentially break it silently, leading to a failure. So I think it's part of what you have to do. If it's not a really industrial product, you have to consider the idea that some people may not use it the way you're thinking they were going to use it. I faced that. I built my own trailer when I was a grad student, when I had time, and I can't sell it because I have to come up with a user manual that says, even though this is big and nice and covered, it's very lightweight covered trailer, aluminum sides and roof, but you can't fill it up. If you fill it up, you'll bust the wheel system and all the suspension. Because I knew I was not going to fill it up. I was going to put bolts in it and different things like that. But if I'm U-Haul and I rent you a trailer, typically you're supposed to be able to fill it up and not get in trouble. It's the same thing with these trucks. So if the box is a certain size, they put the wheels. So even if you got if you're old-fashioned, you got a lot of DVDs, and it's still okay type of thing. So it is an aspect of engineering that I do cover more in the spring, but I'm bringing it up here just because it comes into this type of design on what am I going to do. The other vendors, and I think the client I was working for ended up switching to a steel component just because then it doesn't break. It just deforms for those wheels. So let's talk about that steel product. The main difference here, when you buy these bars, is it was cast and then hot form in this type of shop that we don't have that many anymore in the US, but you keep the steel red hot and you keep reducing it in size. Rolling is the most typical way, and that leads to a lot of plastic deformation. It leads to diffusion that makes your product very homogeneous. It also allows you to control your grain size and all the characteristics that you'll end up with. So the first step in making that raw product is to make billets. Showing essentially here what is coming down the furnace. So you have the liquid steel that goes into these molds where it's cast, and as soon as it's strong enough, it's exposed to the air to cool it off. You want to cool it relatively quickly so you don't have too much difference between the outside and the inside structure of your billet. There are different ways to do it, and we will go through that a little bit. But what I want you to keep in mind, and hopefully, yeah, that shows okay. Hopefully you see it here, how inhomogeneous it is in the first place. So this is a cut view of that big piece of steel. If you take anything out of that hitch mount that I distributed, you won't see that. And the reason is, instead of being this size, it got deformed and deformed and deformed to a point where all of this has changed significantly, and now it's a lot more homogeneous. The aluminum part will have a little bit of this segregation where the properties on the surface, where it starts to solidify, are different than in the core. This is an example given by or thermodynamic professor in course 3, Cedar, was saying that if you make ice cubes at home in your freezer, typically they're not really transparent because you put them in this little casting mold, and it grows and gets to the center, and then you run out, you have extra air or something happens, and then it's opaque. If you go to a restaurant, they will have another system where they essentially keep flowing the water into the mold, and they grow the ice that way, so the ice is transparent. So if we had a way here to essentially solidify from one side to the other, we wouldn't have the same type of segregation or change in the metal, because there wouldn't be this region. So, whatever is left here is what's going to solidify. But that's really what happens in casting a lot. So we see it in a more schematic way, the type of tree zones that you can get in a structure. Now let's try to convince ourselves a little bit on some concepts related to casting. And I don't want you to assume you know a lot about phase diagrams. So I'm going to try to guide you here. So we are looking essentially at phases of this steel-carbon mixture. And the x-axis here is how much carbon there is. So if I'm just over here and I'm looking up, I'm looking for pure iron, what does it look like depending on the temperature? So at cold temperature, all the way to about 730 centigrade, I have the typical alpha phase of steel. And then when I go above this, I transition to the gamma phase, or the austenite. So we have the ferrite up to that temperature, and then we have the austenite. That is a solid to solid phase transformation that happens in steel when you just cool it off or warm it up. It just, essentially, it's a different crystal structure that is stable at that condition. Now you keep heating it up, and you go to a third phase, which we don't need right now to focus on, and then eventually you become liquid at 38 degrees centigrade. So for steel, that's hot. It's not easy to make tough molds, reusable molds to cast steel. And that's why traditionally we've been casting cast iron, which has something of the order of 3 to 5% carbon. And then what you can see is your liquid temperature goes down. So it's just the same way that if you put salt in water in the winter, then you lower your melting temperature. And that is essentially the biggest technological change, and the reason why traditionally we've been using cast iron, and we still do use cast iron for price reasons, and the fact that you can do it at a lower temperature using less expensive material, less expensive processing. This concept of essentially adding, in this case for iron, you add carbon to reduce your melting point. And also, it allows you to make a duplex structure. What you'll see is as you cool this down, it creates a multi-phase material that tends to be higher strength than if you just had one structure in the material. So what I want to say is a lot of times with castings, that's what you do. You don't use a pure alloy. So for aluminum, adding silicon is very common. The part that I circulated is aluminum with something of the order of 12% silicon. So your melting point is going down and you'll be forming a more refined microstructure from the casting than if you just try to use pure aluminum. Now, why are we having this discussion? So I talked about the advantages, right? I say, okay, so if I don't have a pure aluminum or a pure iron, I can cast at a lower temperature, and I'm going to have this mixed microstructure. So the main drawback to this, I'll show you this one first, is you will not form an homogeneous microstructure by default. What you will be solidifying at first is almost the pure alloy because the alloy has the choice. It says, okay, I guess I can take you into my crystal, but if I can avoid you, I'll keep pushing you back into the liquid. And that's really what we call segregation. And we'll go a little bit more in the details here that there's a thermodynamic force that drives this that says, you know what, I don't really want you into my alloy. I'm going to, for now, make almost my pure. The system doesn't worry about what's going to be the equilibrium 500 degrees cooler than where you're at right now. So it's all about the best equilibrium at the temperature you're at. And what really happens, you can see it from the diagram, that at the beginning, this phase here, the aluminum phase in this example, let's say, doesn't want to take a whole lot of alloying element. And as you go further down, the alpha phase here does allow for more alloying element, but everything that started here with the pure aluminum. So you have an excess of all these alloying elements. And the best way to help mitigate that is to cool everything fast. So you don't get the chance for the alloy to move, and the diffusion plays against you in separating the different phases. So we're going to go through two different types of casting processes that will differ with respect to the cooling mold. This is a very intricate one. It's used for very small parts or very sophisticated parts. If you want to make something, even with hollow cavities, something that you couldn't take out of the mold, what you do is you can make that part out of wax, you scribe it, then you put it into a mold, you melt the wax out, and that's your investment. You invested in the casting, and then you can use it to pour the metal in. It's one of the most precise method of casting. It's also more expensive because each time you do have to make you make the part, then you make the mold from it, and then you cast. You're not necessarily interested in a very high cooling rate because you need to fill all that space before it cools down. So, and a lot of times it's not going to be a metallic mold, so you're not looking at a big heat transfer between the mold and the part. It's used for jewelry. So we had a project a couple of years back with Tiffany, and they were using a lot of this type, the exact same type of process for making jewelry. Another kind of slow cooling mode here is sand casting, and that's what this knuckle comes from. So you can't keep reusing your same part to make those molds, and it's very efficient. It doesn't give you a good surface finish, and it's not very high precision either. It's really an inexpensive way to do it. This is a little bit out of order, but I do have these jewelry items. You can see that they have a lot of them. This is the wax pattern mounted, and then when it gets to the process, the liquid metal comes from under and fills all the different cavity at once. So when you're left with the product, you have to cut out the different pieces that you're interested in. You can make just like that, 30 at a time. So when you buy the diamond ring, it's not the process itself that costs a lot of money. It's the raw material, the design, and all that. But making them is, and they will have refinement steps for finishing the surface. But the process itself, when it's controlled, if you start having porosity in this process, then it's a problem. But if it's well controlled, you can get very, very sophisticated, very, very nice details at a small scale. And they were using printing sometimes to make the wax patterns as well. It doesn't have to be done manually here.
Is it completely hollow? Is it like completely hollow from the inside?
On the left here, this is solid because this is all the wax. So you take all of this and you put it in a slurry. It's building up the mold around this, and then you heat it up so you melt all of this. And that creates the channel and all the parts at the same time. Any other questions? Anybody wants to get into jewelry? You can do this in protective atmosphere so you don't get the oxidation. That's very key. The last example I want to put in was a more rapid way to make castings. It's die casting. And I do have a video for it as well. This one. Works.
No.
Not working. Great. It's the main reason I'm showing it is you'll see how fast it's going. Pretty much just this, the very beginning. So they just made one. So the molds are steel, and they're getting cool, and they're getting clean between the cycles. So this thing that came down is just to clean the mold. And you can see everything. Yeah, everybody's like, first of all, it looks ancient, but this is how we make parts today. So if you do go to a shop, it won't look that different from this. The whole process itself can take only a few seconds. And you make plastic parts a little bit the same way, where you inject. In this case, and that's the next part of this here, you do pick up the molten aluminum, and you'll see it being poured down to the system. So they just made one second. This is just another part. It's essentially a manifold assembly with different parts. It's a relatively complex part. If you're using this type of setup where you have the melted metal going into a mold that's cool, for metals, we're going to call it die casting, but we have very similar process for polymers. It's injection molding. So you heat up the polymer and you throw it in the mold. So that's the liquid metal going into it, and you see right after the piston goes. So there's not a lot of time involved into printing these parts. And that's why if you have a large quantity and you can't afford the complex molds, it's a good way to go. It does involve, as you can see, you can have some air contamination. I mean, this is just the liquid aluminum exposed to the environment. And you get better properties than if you do a sand cast, not just because of the surface finish, but because of the faster cooling rate. When everything is surrounded by essentially metal, there's circulation system in these molds to keep them cold. Now, you do need to avoid solidifying too quickly and not having the liquid going all the way to the end of the part. So there's a lot of design into how to make these processes work. But, you know, we talked about this at the beginning, that it is based on economics. So if somebody says, you know, I need to make a lot of these, like aluminum wheels, so I may as well optimize my condition. The one characteristic with the aluminum wheels is to be able to get these fine profiles, you'll have to inject very carefully. And in this example, it's done from the center, and I think that's generally the case. There are other plastic parts in injection molding where you may decide that you're injecting from kind of more central location, but then when two zones merge, you have a mold line. So there's always a trade-off, but in this case, that's one thing they avoid. They really avoid interface by having everything growing from the center to there, but it needs a lot of flow. You need the liquid metal to get all the way to the outside rim. Is it worth it? Yeah. I mean, what else could we do with this wheel? You could forge it, right, to get some good properties. Machining it is a lot of loss. It's not impossible, but it's a lot of loss of material. So I think that's one example. They've used different kind of alloys for doing this, but in the end, you do need to lower the properties as opposed to if it was forged. So if you decide you're using a steel forged wheel, you're going to be able to allow a lot more stress per square area, and therefore, if it's really optimized, sometimes, and you may have heard of this for bicycles, one or the other is just about the same, because with the steel, you keep optimizing it, you get better joints out of it, and you're able to use it almost as you would for aluminum. But this is easy, right? If it's a large quantity and people like the look, you're in business, and you can change the mold by step. You always need to have enough heat so you don't fully solidify before you get the alloy all the way to the outside edges here. Sometimes you'll have some excess metal that you'll cut back. And I think you know, even for that casting, you can put a little extra step of machining at the end. So I hope you get to see a little bit where we're going. Not all of the kind of general concept apply as we move forward, but I want to make sure I cover this level of, you know, this looks like this looks like that. Next time on Monday, we'll go a little bit more to the details on what happens during casting, and I will start deformation processing Monday as well. So I hope you have a good weekend, and thank you for the participation. I need to, you know, speak less and have you ask questions.
Thank you.